So, just a really quick review. A force is a push or a pull. It is an attempt to make something change its motion or its shape or form. Now, the emphasis has to be on attempt because forces can be opposed by other forces, and so something can be in equilibrium. They don't Force doesn't necessarily cause a change, even though it's attempting to do so. And this fact of equilibrium, the potential for equilibrium, two forces opposing each other, kind of interferes with the topic that we want to learn about today. People get confused between equal and opposite forces acting on the same object and what we're going to talk about today, which are equal and opposite forces acting on different objects. So, in the simplest sense, a force is a push or a pull. It is an attempt to change the shape or form of an object. And we talked about acceleration equals force over mass and several other things connected to concepts of forces. You can have action at a distance forces like gravity or contact forces like pulling on a rope or something. The twist we're going to put on the concept of force today is that there is actually no such thing as a force. It's always a pair of forces. Anytime you create a force, a second force is automatically created, and there's nothing you can do about it. Forces always occur in pairs, they never occur by themselves. So, our big idea for today is for every force, there is an equal and opposite force. Think about this. Maybe you've hammered a nail or you've seen somebody hammer a nail. Obviously, you move the hammer, it hits the nail, and it drives the nail into the board. But one of the things we learned about in an earlier lesson is the concept of inertia. Once that hammer is moving, it should continue to move in a straight line at a constant speed. But hammers come to a stop when you hit a nail. Obviously, a force must have acted on the hammer. So while the hammer exerts a force on the nail exerts a force right back on the hammer. Now, it's kind of hard for some people to think of inanimate objects as being able to exert forces because they don't have um, muscles, they don't have engines, with obvious fuel consumption and so forth. But you don't have to be an inanimate object in order to exert a force. So think about this. If you push on the wall is pushing back on you. Or think about this. Here's a better way to think about it. Most of you are sitting down right now, or maybe you're lying down on a bed or a couch. What do you feel on your backside? I'm sitting in a chair, and what I feel on my bottom is the chair pushing on me. I don't feel myself pushing on the chair. That's what the chair feels. What I feel in my body is a force acting on me. I feel it pushing up on me. It gets to me every now and then. I have to get up and walk around because I can't stand all that force that's acting on me all day. So was um, this idea that for every force there is another force was known to Isaac Newton. And I told you earlier the story that Isaac Newton wrote basically three books. Um, Collectively, they're called by the shortened name of the Principia. It's Latin for principles, or the principles of nature. Basically, he put together everything he could think about physics and about math, and he put them into these three books. Well, in the preface of that book, he put three axioms. In other words, three truths or ideas on which he was going to build other concepts. Those axioms we now call Newton's three laws. So the third law is what we're talking about today. It is whenever an object exerts a force on a second object, that second object exerts an equal but oppositely directed force on the first object. Or in more simplified terms, people like to say for every action, there's an equal and opposite reaction. Now, Newton's third law describes a relationship. It describes an interaction. We have both an action force and a reaction force. A very important point is that you can't have one without the other. And so it really doesn't matter which one you designate as action or reaction. They are equal in size, but they are oppositely directed. Newton referred to them as a mutual action. That's different from interaction. A mutual action means it's shared. They are a shared experience. Every force is it's got a partner, okay? And this is an automatic given. It's always true. It's just the way the world works. But it's kind of confusing. If neither force exists without the other, how do they come into being? Well, like I said, it's just the way the world works. There are basically four features to this Newton's third law. It's very easy to say. For every force, there's an equal and opposite force. For every action, there's an equal and opposite reaction. It actually has four features. One, the two forces are equal in magnitude, equal in strength. Two, they are exactly opposite in direction. If you push to the right, something pushes you back to the left. This one's a little mind-blowing. They are created at exactly the same moment. There's no lag, okay? You don't push against something and then it decides to push back against you. It's automatic. So there was no force there before, and all of a sudden there's a force. It's really kind of strange when you think about it. It requires no time. And this is a big key idea. This is where people sometimes get really confused. If you have two forces, they're equal but oppositely directed. Shouldn't they cancel each other out? They act on different objects. One force is on one object, the other force is on the other object. So each object then does whatever it does when that force is applied to it. So the two actions that occur because of the two forces are independent of each other. Think about walking or running. Okay, you ever think about that? How do you walk? You push against the ground. That's a force you're making on the ground. What does it have to do with you? The ground pushes back. It's the force applied to you by the ground that makes you go forward. So forces always occur in pairs. You can't help it. If you push against something, it pushes back. Now, when the ground pushes you, you move. When you push the ground does not apparently move. Why is that? That's kind of weird, but we're going to talk about that in just a minute. The other day, my wife, she likes to swim. She swims 3 days a week. And the other day, she wanted to swim a mile. And she needed somebody to count laps for her because that's a lot of times going back and forth in the pool. And she wanted somebody to count in time for her. And so I went at 6 o'clock in the morning to the pool and I watched my wife swim. And of course, I was thinking about physics as I was watching. When she pushes backwards, somehow she goes forward. What she was doing is she was pushing backwards against the water, and the water was pushing my wife forward. It was an opposite force on her body. If you think about driving, how does your car work? It's not because it has an engine, quote unquote. It's because it pushes backwards. If you look at this little diagram that I have on the screen there, if you think about that car going to the right side of the screen, think about how the wheels would have to turn. They turn clockwise, just like a clock, right? By the time the wheel gets down to the road, it's actually moving backwards. It's pushing backwards onto the road. How does a car move forward? The road pushes it. If you push backwards on the road, just like you push backwards with your foot to walk, the road pushes you in the opposite direction. you have to be able to complete the push in order for it to be able to push back. So if there's no friction, if there's ice, for example, then the tire has no friction against the road. The road can't push back because the tire can actually push on the road. It's kind of a weird thing to think about, that the two things might be touching, but they can't really exert a force on each other if there's no friction in that particular case. Now, forces don't have to rely on friction. Here's another example. This is Wile E. Coyote, and a boulder is falling down on his head. Okay. Now, obviously, the boulder is being pulled downward by gravity. Gravity is a force. There must be an opposite force. Where is it? Believe it or not, if you call one force the Earth's gravity pulling down on the boulder must be pulling up on the Earth. Not only is it pulling up on the Earth, but it's pulling at the same time by the same amount in the opposite direction. That's what Newton's third law implies. This is really kind of weird and hard to understand sometimes. Think about this question. You've heard of dynamite or TNT. They use it in the Roadrunner cartoons. If you ever watch one of those or some of those other violent cartoons on TV, they blow things up with dynamite. Does dynamite contain force? A force is an interaction. It's not a thing. All right? You can't actually have a force. You can exert a force and you can have a force exerted on you, but you don't actually have a force in the sense that we're using the term. Rather, what you're doing is you're confusing force with energy, what we're building up to later on this semester. A dynamite stick has energy. It has potential to create something called a force. All right? So that's kind of a little weird thing. Now, Isaac Newton was actually in a quarantine situation, and he was outside of a town in a country estate. He wanted to get all his ideas written down, and so he was working on his masterpiece works there. But he wanted to have a sort of isolated spot, not only so he could stay healthy, but just so he'd have a place to think, kind of a quiet place to think. And he was looking out the window one day, and he saw an apple fall to the ground. It didn't actually hit him on the head, as is often shown in cartoons, but he saw an apple fall. And then he kind of looked up, and there's the moon in the sky. And so this gave him one of his greatest ideas. He didn't discover gravity, but what he did was apply it universally. He said, if the earth pulls the apple down, then the earth can also be pulling the moon down. Why doesn't the moon crash into the earth? It's a two-dimensional vector problem that we skipped over. We didn't go into projectile motions, and so I don't want to go into the details right now. But basically, the moon is moving left to right at the same time that it's being pulled down toward the ground, and it results in a more or less circular orbit around the Earth. So what Isaac Newton did was he said, the Earth is pulling on the moon, and it makes it go around and around. Well, now Isaac is saying for every force, there's an opposite force. So does the moon also pull on the Earth? Does the moon pull on the Earth? And if so, which of those pulls is stronger? The Earth is much bigger. I guess I should have thrown that in there somewhere. Question. So here is one way to think about it. If you were traveling, say, from New York to San Francisco, which distance is greater? Going from east to west or from west to east? Well, in terms of displacement, straight line, obviously it's the same distance. That's what we're saying with forces. Okay? Doesn't matter which way you point the arrow, they're equal in size. So, yes, the moon is pulling on the Earth, and its pull is the same size as the Earth's pull. But that's weird. How come the moon is able to be pulled around the Earth and the Earth isn't pulled around the moon? Well, believe it or not, in a sense, the Earth is, in fact, pulled around the moon. If you were not standing on the Earth, if you were outside the, say, standing on the sun, looking at the Earth and the moon, you'd actually see them kind of dancing around each other. But the Earth doesn't move anywhere near as much as the moon does. And we're going to get into that, but it's basically because the Earth is so much bigger. So let me put it to you. Let me just do this little demonstration, and maybe you'll get it. Here's two objects. Let's call one the moon and the other the Earth. But let's pretend like they each weigh 1 kilogram. They have a mass of 1 kilogram. Okay? They have a gravitational pull on each other because that's what Newton said about gravity. It's a universal force. Everything that has mass has gravity. It's pulling on every other thing. So if the one on the left is pulling, the one on the right is pulling equally and in the opposite direction, right? 1 kilogram pulling on 1 kilogram, so the two forces are obviously equal. Well, now let's pretend like that object on the left actually outmasses the one on the right. Maybe it weighs twice as much, right? The one on the right must feel a greater gravitational pull because the one on the left is now more massive. Follow me so far? Now think about this. You see that kilogram that I just added on the left? It also experiences gravity. It pulls on the 1 kilogram mass, just like the one below it does. They have equal but opposite effects on each other. Every kilogram pulls on every other kilogram the same. Even if that 1 kilogram already has another force acting on it, the other kilogram doesn't know that. So what if we had, say, a third one there? Well, the one on the right would have 3 equal tugs to the left. The one on the left would have 3 equal tugs to the right. So if this one on the right is the moon, which has a small mass, and the one on the left is the Earth, which has a large mass, they can and do, in fact, exert equal forces on each other. The reason why people don't understand that is because of the effects of those forces. The forces are acting on two different objects. This 3 forces acting on the moon will make it move much differently than the 3 forces acting on the Earth, which is more massive because of mass. See, most people think of mass as being, they might define it as mass is the amount of matter in an object. But a much better way to define mass in the physics sense is it is a measure of an object's inertia. In other words, mass tells you how much that object is going to resist moving. The 3 kilogram object will resist the pull 3 times more. It will be affected 3 times less. That's simple math. A given force acting on a small mass produces a greater acceleration than the same force acting on a large mass. Let's think about it in terms of like a cannon. You ever see a cannon fire? Well, one thing you don't want to do, though, is stand obviously in front of the cannon, but you also don't want to stand behind one because when it shoots the cannonball forward, the cannon does, in fact, move backwards. It doesn't move as far and it doesn't move as fast because the cannon has much more mass. But there is a force exerted on it, and it is in the opposite direction. So the cannonball will move a lot compared to the cannon. They'll move in opposite directions, but you've got to take their masses into consideration. If you look at it this way, acceleration is force over mass. Well, if you have the same force, so I drew the same size F, okay, but you have different masses, you're going to produce different accelerations. The cannon's mass is very large, and the mass is in the denominator. It's an inverse relationship to acceleration. So if you make a very big denominator, you're not going to get a very big acceleration. And that goes back to what we were talking about like when you push against the ground pushes you back. You go forward. Why doesn't the ground move backwards? The ground has a infinitely bigger mass than you do. So it in fact does move backwards, but you could never measure it. It would be such a small movement that you couldn't tell. Okay. So the change in uh, velocity, in other words, the acceleration of the cannonball will be much greater than the change in velocity of the cannon. Now, in this case, we're just shooting off a single cannonball. Okay. What if you could fire off a lot of them all at the same time? Well, then we get into rocket science. So I'm going to build up to that. So again, let me go back to this boulder idea. I showed a boulder earlier falling on Wile E. Coyote, and I asserted to you at that time that if the boulder is being pulled down by gravity, it is pulling up on the Earth equally. But you will notice the boulder fall, you will not notice the Earth move up because the Earth's mass is so much bigger. Okay? So acceleration is not only proportional to the net force, it is inversely proportional to the mass. If you have the same force acting on different masses, it will produce different accelerations. Some of those accelerations may be so small that you could not even measure them. So I mentioned rockets a second ago. If you ever taken like a balloon and blown some air in it and then let it go and watched it kind of twirl around the room, a lot of people think that when that air is coming out, that it's some kind of interaction with the air around it that makes the balloon twirl around. That's not really what's going on. The balloon is elastic and it has some stretchy forces, you might say, and it pushes the air inside the balloon, it pushes it backwards. The air coming out of the back end of the balloon is what pushes the balloon in the opposite direction. It's not the air around it, it's the actual air in the balloon that pushes back. When the balloon pushes on it, it pushes back. Same thing happens with rockets. But people see a rocket launch and they think that the rocket is going up because it's pushing against the ground. That has nothing to do with it. If you look right at the tail end of the rocket, you see that fire right there. What that is a bunch of gases that are being produced by a chemical reaction inside of the rocket, and it's producing a bunch of gas molecules and throwing them down. Those gas molecules throw the rocket up. Each individual molecule can't move the rocket very much. But if you get billions and billions of molecules collectively, they can get a big enough force to make the rocket go up. But it has nothing to do with the surrounding air or the ground. Okay. It's a common misconception that the rocket is somehow propelled by the exhaust gases hitting the ground or hitting the air around them. But in fact, a rocket would work better if you got it out of the air, because then there would be no air resistance to slow it down. So it's the rocket itself throwing something backwards. That thing it throws backwards, those gases throw the rocket forward. Each individual little gas molecule can't move it very much, but lots and lots of them can actually make the rocket move. It's kind of like saying, if you had a penny, you don't have very much money. But if you had a billion pennies, you know, now you're cooking. Okay. Now you're a wealthy person because each individual penny is not worth much, but a bunch of pennies can add up. Same thing with forces. A small force may not add up be very effective, but a lot of them can add together. One last moving, since we're talking about moving and action reaction, how do airplanes fly and birds fly and helicopters fly? It's the same thing. It's Newton's third law. Now, obviously, an airplane goes forward because it has engines that are pushing air backwards. And so everybody can kind of understand that. If you push the air backwards, it pushes the airplane forward. But how does the airplane go up and down? Well, it has to be the same effect. You've got to push air down in order for the air to be able to push you up. So if you take a look at the way the wings on an airplane or a bird or a helicopter, if you take a look at the wings, what you'll notice is in order to go up, they have to knock air down. So the air hits the front of the wing and bounces down, it will push the airplane up. If you get enough air pushing down, then it will be able to overcome the gravity force and push the airplane up. Okay, and we call that lift. Now there is another effect that goes on that also has to do with air, has to do with air pressure, but we're not going to we're not going to dwell on that Bernoulli's effect today. So what this is going to build us up to is this idea right here, the idea of systems. What really gets confusing about Newton's third law and these equal and opposite forces, like I said, people just imagine if they're equal but opposite, they must cancel each other out. But this big key idea I'm trying to get across to you, the two forces that are created at the same time, equal in strength, opposite in direction, are acting on two different objects. The two forces you got to think of like this. One force is acting on the object, the other is created by the object. Okay? So you got to distinguish between those forces acting on something and created by something. They happen at the same time. But whatever force is acting on the single body, that's what you got to look at as far as determining what happens to that body. So that's where we get into this idea of systems. Basically, what we're going to do is we're going to sort of put things in a box. We're going to draw a little line around things. And we're going to say, all we care about is what's happening inside the box. Then we'll be able to isolate these forces and see what's going on. But we always have to remember that even though in the box we're isolating forces, in the real world, they're not isolated. They're occurring in pairs.